Welcome everyone to today's tutorial. Today we'll be talking on the adjoint of a matrix, and we are going to be able to use the adjoint of a matrix by the time we fully understand what the adjoint of a matrix is and how to compute the adjoint of a matrix to get the inverse of a matrix. And particularly we'll be looking at a square matrix, and that will fall on a 3 by 3 order matrix, a matrix that has 3 rows and 3 columns, a square matrix. Here I said the adjoint of a matrix A, denoted by this adjoint A as a symbol, is a transpose of the matrix formed by substituting each element of A by its cofactor, which means the first thing that we are going to do when given a matrix, a square matrix of size 3 by 3, is to get its cofactor. And cofactor of an element in a matrix is a signed determinant of the submatrix obtained by removing the row and column containing the specified elements. I also gave here the meaning of what a minor is in matrix, and I said here that minor of an element is the determinant of a square matrix, of a square submatrix obtained by deleting the rows and columns in which that element lies. So actually the difference between minor and cofactor is that minor doesn't have the conventional signs that follows each element in a matrix, whereas cofactors must have the signs that are assigned to each element in a matrix. So I'm going to explain in a moment what this definition talks about. So if I'm given a matrix A equal, this is a 3 by 3 matrix, 2, 3, 5, 4, 1, 6, 1, 4, 0. So we can see that it has 1, 2, 3 rows and has 1, 2, 3 columns. So this is a 3 by 3 matrix. Now the first thing we are going to do is that we are going to get its cofactors. We can actually get the minors first, and then once we assign the signs, once we allocate to each of the elements in this matrix the signs, then we'll have the cofactors. So let's start. Now we'll start with the first element, so moving through all these elements to the last, which is 0. So get the minors of each of these elements. So beginning with 2. And now remember what the definition says. If you want to get the minor, if you want to get the cofactor, but I'm going to be more specific on cofactors. I'm going to use cofactor here because that's what will finally give us the result we want in this example. So I'm going to start with this 2, and I'll delete the entire row containing 2 and the entire column. So I'm left with this submatrix. This is a submatrix. So I'm going to take the determinant of this submatrix by multiplying the elements in the diagonal. So 1 times 0 is 0 minus the product of the elements in the second diagonal. 6 times 4 is 24. Okay, and then the next thing I'll first of all compute the determinant of each of these matrix in respect to their cofactors. So for 3, I will delete this row, I will delete this column, so I'm left with 4, 0. So I'm multiplying now the elements in the principal diagonal. These are the elements in the principal diagonal. 4 times 0 is 0, and then minus the product of the elements in the secondary diagonal. 6 times 1 is 6. Now each of these elements, the cofactor I get, or the minor I get, I said I'm going to work with the term cofactor. So the cofactor I get is in the corresponding position that I'm also arranging it in. Okay, so next is with 5. I'm going to delete all these elements in the row that contains 5 and the elements in the column that contains 5. I'll take the product of, okay, that's actually the second diagonal. Supposed to take the product of the principal diagonal first. 4 times 4 is 16, minus, and then the product of the second diagonal. 1 times 1 is 1. Okay, so I'm going to work on 4. Delete this column, delete this row. So I have 3 times 0 is 0, minus 5 times 4 is 20. Okay. And then for 1, we delete this, delete this. So I have 2 times 0, 0, 1 times 5 is 5. Then for 6, 2 times 4, 8, minus 3 times 1, 3. Each of the elements I delete, there will be no need of adding them in my products. I'm not going to put them among the elements I'll take the product of. So in the last row here, 3 times 6 is 18, minus 5 times 1 is 5. Okay, now I'm in 4, so I'll delete all the elements in the row and column that contains 4. 2 times 6, take note, 1 is now among here. 2 times 6 is 12, minus 5 times 4, 20. Okay, now the last element, which is 0. 2 times 1, 2. 3 times 4 is 12. Okay, now I said I'm going to use the cofactor, and cofactor is the signed determinant. So the conventional sign the element takes. I'm going to do that for a 3 by 3 matrix. It starts with positive, it alternates through positive, negative, positive, negative, positive, negative, continues until the end. So that's the signs which will allocate to each of these elements. So by the time we finish with all this, we've gotten the cofactor of A, of matrix A. So I will assign these signs. Plus, I assign them here. Minus will be here. Minus will be here. Plus will be here, according to their respective positions. Okay, so the first here is 0 minus 24, so that's minus 24, and minus 0 minus 6. Minus minus is plus, so I have just 6, and then 16 minus 1 is 15. Minus 0 minus 20 is same as minus minus 20, and that's positive 20. 0 minus 5 is minus 5. 8 minus 3, that's 5, and then here should be minus 5. So it's very important we obey the principle of board mass. That's bracket first. We have to work within the bracket before using any other expression outside the bracket. Okay, so next here is 18 minus 5. 18 minus 5, that's 13. Minus 12. Okay, oh, sorry, I was about to make same mistake. 12 minus 20 is minus 8, and then minus times minus is plus, so this 8. 2 minus 12 is minus 10. So this is my final evaluation. I'm going to wipe this off. Okay, and then I'll take this up. So this is my cofactor. A is equal to, this is my new matrix. The next thing I'm going to do, I can use this. This is actually not A, this is a new matrix. I can call it B because it's not the same with A here. So the next I'm going to do to complete my adjoint of A is I'm going to take the transpose of matrix B. So BT will be equal to, all these will be changed to a column. Same with all other rows, they'll be changed to a column. And then 13, 8 minus 10. So this is my adjoint of A. As simple as that. Next, I'm going to do on this tutorial is that I'm going to compute the inverse. How do I get the inverse of this matrix A? Now, in this original matrix A, the first step to take to get the inverse is that I'm going to evaluate the determinants. And how do I do that? Take the cofactor of elements in any rows in this matrix. So I can take the cofactors of elements in this first row, or I can take the cofactors of elements in this second row, and as well I can take the cofactor of elements in the last row. But I'm going to use the elements in this first row to get my determinant using cofactors. So let's do that. Bring it down. Okay, so I have A to get my determinant. Determinant of A is equal to, beginning with 2, I'm going to delete the column and the row, so I'm left with 2 times 1 times 0, which is, or let me just use a bracket, to also save time. 1 times 0, that's 0 minus 6 times 4, that's 24. Remember the signs each of these elements take: plus, minus, plus. So the next will be minus 3, and I'm deleting the elements in the same row and the same column. So I have 4 times 0. 4 times 0 is 0, and then 6 times 1, that's 6. Minus should be in the middle. Okay, let me make that more clear. 0 minus 6, and then plus 5 brackets. Four times 4 is 16, minus 1 times 1, 1. So computing the determinant of matrix A, 0 minus 24 is minus 24, and 2 times minus 24 is minus 48. 0 minus 6 is minus 6, and minus 6 times minus 3 is positive 18. Minus times minus is plus, and 3 times 6 is 18. Next, I have 16 minus 1 is 15, and 5 times 15 is 75, is positive. So minus 48 plus 18 plus 45, the answer is equal to 45. Therefore, the determinant of A is 45. So having gotten the determinant of A, which is 45, I'm going to write down the formula we use in getting the inverse of a square matrix, a 3 by 3 matrix. So the inverse of a matrix A is denoted by this symbol A inverse, and it's equal to 1 all over the determinant of A times the adjoint of A. So this is actually how we can get the inverse of a square matrix. The inverse of a matrix. Now I'm going to bring out the adjoint of A from what I've solved previously, which is this matrix. First I can erase all these. I think that should be useful for that's my original question. Let me erase all this. To make more space. Okay. Okay, so I have my adjoint of A. I'm going to represent it here. Minus 24, 20, 13, 6, negative 5, 8, 15, negative 5, and negative 10. This is equal to my adjoint of A, and I'm going to put in my determinant, which is 45. I've already wiped that up, but my determinant of A is 45. So this is the inverse of A. So this is how we can calculate the inverse of a matrix. Thanks for watching.